Uh, is my slide visible?
Yes.
Yep.
Okay, great. So, warm welcome to everybody. Good afternoon, good morning. Uh, Welcome to this workshop on RISC-V. Uh, the brief agenda for this 1 hour talk is I'll start by introducing RISC-V. If you are already in RISC-V, this is just a precursor on what is RISC-V, the ISS specification on the privileged and non-privileged spec. Then I will go into the mainly the verification part of the talk, which is like starting with fundamentals of processor core verification. Uh, Talk briefly about how you develop or how the random test case generator would look like, because that's a very important part of verifying your processor. I'll talk briefly about memory subsystem or cache verification. And then finally, I will wrap it up with the RISC-V debug specification and verification and conclude. Now, of course, it's a very short duration. There are many topics, so I'll try to keep it mainly focused on some of the core concepts. And then once the talk is done, we can take some question and answer. Okay, so introduction to RISC-V. I think everybody is aware that there is a big paradigm shift in the hardware industry with the adoption of open source RISC-V ISA. RISC-V had featured in the top 10 technology trends last year in the MIT Technology Review. Continues to be a very hot topic across the world in the hardware as well as software domains. Uh, One of the main reasons why RISC-V got adopted, especially in the embedded products, apart from licensing, is also the geopolitical situation. As you already know, RISC-V International is in a neutral place in Europe, and that actually enables a lot of different companies across the world, different organizations, different individuals to come and contribute to RISC-V. So this, if you see as a something like a similar trend in the software industry was when Linux came in, right? So we had multiple flavors of Unix like HP Unix and AIX and Solaris. And initially there was some trouble when Linux came in. It was not the best machines that you would get. But over time, Linux just took over the entire computing, right? So hopefully RISC-V is also going in the same direction. And if not, it will take over the entire portfolio. It will be a big movement as it enables so many individuals and organizations to contribute without paying a hefty license fee, right? So that's to an extent, it opens up the entire hardware as well as software innovation in the embedded products as well as the high performance products. So in nutshell, RISC-V defines the architecture standards, including for example, the instruction encoding and format. So you mainly have the standard instructions that come from RISC-V. It will describe the register file. We'll go through that. Describe about things like exceptions and interrupts, which is in the privilege spec. It will also talk about things like debug and trace. It talks about things like toolchain specific, like the application binary interface. For those who are not aware, this is how the application binary interface is the spec, which basically defines when you write your C code, how does it translate into your assembly code? For example, how does a function call happen? What registers are used to pass arguments and all these things, right? What it does not define is a hardware implementation of any processor. So this is where everybody of us can innovate, and RISC-V will define the standards. All software, all tools, all hardware that comply to the standard would be able to talk to each other. Okay, a brief slide on the RISC-V processor development effort in NXP. We have been doing RISC-V course in NXP for last several years. The main focus have been differentiation in our products in edge computing through industrial grade cores. It's not only the licensing fee which matters, but the big thing that you can do with RISC-V is have custom ISA extensions. For example, in places like security, in domains like AI/ML, in safety, in vector, DSP. So this enables many organizations, many SOCs, many architecture teams to put in their secret sauce, which you cannot actually do with standard processors. And it has been highly successful in various product lines in across NXP. Primarily, it has been targeted to acceleration subsystems and helper cores, and that's where RISC-V has been going in most architectures across the world. There are places where it is going as the main application core, as well as in the high performance domain. But the bulk of RISC-V is going into these accelerator subsystems and the helper cores on your SoC. They are quietly there, but they are there in large numbers. And NXP has a rich legacy of building microprocessor architectures. For example, we were building PowerPC a decade back. And so for many of these companies who have a background of building microprocessor, it's a no-brainer to actually invest in RISC-V and leverage that know-how within the organization. Okay, so now let's get into the nitty-gritties of processors ISA specification. So RISC-V defines what is called, the first thing is the standard extension. And if you see this chart on the right, it gives you the basic extensions, which are very popular. I stands for the integer extension, M for the integer multiplication division. Similarly, there are atomics, floating point. There are combinations of that. For example, you have the G, which is the general purpose, which is a combination of I, M, A, F, T. So each of these extension is a collection of instructions. For example, I is a collection of say 40 instructions, M is a collection of 10 instructions, and you just add them up, you get a you get a collection or some sort of what we call profile in the RISC-V world. Now, there are many popular ones. Obviously, the main thing that you require, the mandatory one is the integer extension. You must have that. All the others are actually optional. So you can have RV32i. RV32 stands for 32-bit RISC-V processors. RV64 stands for 64-bit RISC-V processors. And you can have multiple combinations of them. The compressed instruction is also very popular in the RISC-V world, which is a 16-bit instruction. RISC-V instructions, both RV64 and RV32 by default are 32-bit. The opcode is 32-bit, apart from the compressed ones. So this is how RISC-V defines all the standard extension. And also RISC-V International provides a space in your address space for custom extensions. And that's where you can do all the secret sauce that you want to do. Now, coming to general purpose registers, RV32i, RV64i, they have 32 integer registers. RV32E, which is a flavor doing very small microcontroller cores, you can do 16 registers. So if you need a low power, low area core, you can live with 16 registers. The performance isn't so bad. There are optional floating and double registers. Optional in the sense you can also do float using integer GPRs, general purpose registers, and that is called in RISC-V terminology the ZF in X. That means the F in X register, right? So that's the extension. X0, which is the register 0 in RISC-V, is a constant 0. And so this is very different from any other architecture. Everywhere R0 is a register, but in RISC-V, it's not a register. It's a hardwired 0, constant. So on the right-hand side, I have basically put in this chart, which is basically the register. The first column is the hardware name. The second column is the ABI name or the software name, right? And then third column describes what these registers are used for as per the ABI spec. and then where it is saved, right? Whether the caller function is saving it or the callee function is saving it. So for example, some of the important registers are x1, which is the return address from a function. Then stack pointer is x2. So if you RISC-V maintains the stack of your program, so when you actually compile the C program, the entire stack pointer is tracked using the X2 register. And you would mention it, most of the tool chains, you will see it as SP. Similarly, there are other registers. Then there are, for example, X10 to X17, you have function arguments and return values. So this is when you write a function foo and you pass two arguments. The first two arguments will go as X10 and X11. And then there is a return value that will come back in X10. So this is how RISC-V ABI defines how to use the registers. And this is the complete set of general purpose registers. Okay, now going from general purpose registers, we look at the control and status register. In short, we call it CSR. Now, there are a lot of them, so I have just mainly listed down the main ones. If you see from the top, the initial left-hand side, the initial few ones are mainly ID registers, right? That really don't do anything. It's basically for saying what's your ID, architecture ID, vendor ID, thread ID, blah, blah. The most important register here is M status. M status is actually tracking the state of the processor in machine mode. The M stands for machine mode, and we will have similar CSRs in other privilege modes. And we will go through M status in more detail in the next slides. Then there are other registers for interrupt delegation. There is a concept in RISC-V where you can actually delegate taking an interrupt, not in machine mode, but you can delegate to take in supervisor mode or go to user mode. So those type of things can be done. So these are the delegation registers. There are interrupt enable registers. There's a machine trap handler base address is given by MTVEC. So these are different kinds of registers. When you actually take an exception, that's where the machine trap handling registers come into the picture. And I'll go through that in more detail in a slide later. So we'll just park it here. There are registers related to the physical memory protection block in RISC-V, which is another name for MPU, right? If you are familiar with earlier architectures, what we used to call MPU is PMP in the RISC-V world, and there are CSRs where you can define the addresses and the access permissions, and you can get the PMP. On the right-hand side, coming into your performance counters, for example, cycle, instruction retired, different types of counters. You have the higher part of the cycle, like the upper 32 bits of cycle and instruction retired, all these things. Finally, you will have something called the trigger and the debug register. So, for example, the T-select, T-data1, and blah, blah, these are trigger registers by which you can set breakpoints and watch points in your for debugging your code. There are debug mode registers like the DCSR, which is the debug control and status register, DPC being the debug PC, and then there are other similar registers. Now, as there are M registers in machine mode, there are similar registers in supervisor mode. So if your processor is supporting multiple privilege levels, you can have multiple sets of these registers which are mentioned as M. If it is not supporting any privilege level, right, you can have anything, like everything is in machine mode. There is no concept of privilege level. All you will have is machine mode registers. So this is a bit on the instruction format. Instruction format here is like I have shown like 32-bit normal instructions here. If the last two bits of a 32-bit instructions are 1, 1, is 1, 1, then it's a 32-bit instruction. If it's not 1, 1, it's a 16-bit compressed instructions. So that's how you can easily decode whether an instruction is 16-bit or 32-bit in the RISC-V world. The register locations are in fixed places, and that makes the decoder design much simpler. If you compare with some of the previous generation ISAs, these can be rather complicated. This can be all over the place, and you need to use very sophisticated Carnot map solvers to actually solve that, right? I mean, your decoder becomes very big. In the RISC-V world, this is very nice. You have very fixed places for your registers. There are groups of instruction encodings like types, for example, R type, which is the register as shown in the first encoding format. Then you have the immediate type. Then there is the S type or the store type, and then U type, which is the loads with immediate. And I mean, there are other types, but I've just shown the basic types here. You can look at the layout of the instruction and easily design a much simpler decoder. One of the reasons RISC-V tends to be lower power, I mean, sometimes you hear that is one of this reason. Now, of course, it's not true. The entire power is determined by decoder, but given the decoder is simple and not so complex, it does tend to be much lower power compared to other more complex ISS. Some 16-bit instructions only use X8 to X15, and because in a 16-bit instruction, you don't have too much bits, right, for encoding your registers. So you can't use 5 bits for registers. So you just use 3 bits, and there the inherent understanding from 0 to 7 is 0 starts with X8 and 7 is X15. So that's how RISC-V has actually compressed it into these instructions. There is a reserved opcode space for custom extensions. Okay, so now coming to a very brief summary of the standard instructions. There are loads and stores, very common. You can have word, half word, byte within the loads and stores. You have shifts, arithmetic, logical compare. These are very common in any RISC architecture, whether it's ARM or PowerPC or MIPS, you will find all of them. Branches are, you can compare any two GPRs and branch. This is somewhat different from some of the other architectures. In some previous generation RISC architectures, you wouldn't be able to do that in one instruction, right? You would set a condition flag, comparing, and then take the branch. Jump and link is also like very similar to PowerPC. You can jump and link. This is for function call and return. So you jump and link the register, the PC that you need to return, and from the function return, you jump back to that link register. So this is for function call and return. Then there are multiply instructions. These are normal standard instructions, divide and remainders, CSR accesses. So to write, set, clear CSR registers, you have different types of CSR instructions. There are atomic instructions, including LRSC. LRSC is very popular in many other architectures. So LRSC stands for load, reserve, store, conditional. RISC-V obviously defines more complex atomics, but LRSC is very popular across all RISC architectures. For privilege specification, you have different types of instructions, like eCall is similar to a syscall. eBreak is mainly used for doing software breakpoints in your code, where you patch an instruction with a eBreak instruction, and you can break and go into debug mode or go into exception. MRET, SRET, these are written from exceptions. WFI is a special instructions, more like a low power instructions where you wait for interrupt. So you can execute WFI and just the CPU stalls. And once an interrupt comes, you can either go to a handler or you can start inline again. So WFI is a nice low power instruction for doing. So there are lots of other extensions, but I just compared, I just put in some of the instructions that are popular. Coming to the privilege spec, as I said before, you can have multiple privilege levels. You can have only machine mode. You can have machine and user mode. You can have machine supervisor user, or you can also have the hypervisor when you have the guest OSs. So these are the 4 privilege levels, starting from machine mode being the highest privilege level. So you start off when you boot a core, right? The boot code starts in machine mode, and then you move to higher and higher levels depending on where you are. For example, Linux would be running in the supervisor mode operating system. your user applications would run in the U mode or the lowest privilege mode. Now, for those who don't understand what is a privilege mode, think of it as access permissions, right? There's nothing fancy about privilege mode. It's just whether in that mode, the CPU is able to access some registers or access some memory addresses, right? So in machine mode, you can access anything. You can go to any register within the core, you can go to any memory address, and it allows you. As soon as you go to lower and lower privilege modes, things start stopping you. So this is how you can actually think of as privilege levels, right? The simplest way to look at privilege levels is how you are isolating all your user programs from corrupting each other when you are running under OS, right? This is how, by using privilege levels, you can make sure that each guy has its own address space and own set of resources. On the right hand side, I have put the M status CSR. This is the most important register. Starting from the interrupt enables, the machine supervisor and user mode interrupt enables. It also stores the previous interrupt enable as well as the previous privilege. Now, how it does is when you, okay, I think I have that slide later, so I can cover that later. But this is basically the structure and the main bits of the M status CSR. So now coming into so we got a brief background on the RISC-V ISA architecture, right? The ISA specification. Now we come into the how do you verify, and from a verification perspective, how do you verify a RISC-V processor? So the fundamental technique that you use in most cases to verify a processor is something called lockstep compare, right? So you verify result of instruction execution against a golden reference model or an instruction set simulator, which we call ISS. And this duty, which is your RTL or the design of the microprocessor, and the ISS, they run in lock and step. So you execute one instruction on the DUT and you execute one instruction on the ISS, compare the results. The results don't match, you flag an error. So this is the simplest way and the best way to verify any microprocessor. It hides all internal microarchitectural details of instruction execution. So it and works for all types of processors. Whether it is scalar or superscalar, in order or out of order, once you basically take the result from the completion or the write back stage of pipeline in the DUT, that should match against the ISS. So here, for example, I have a simple diagram of an in-order processor, pipeline processor, where you have the instruction fetch, decode, execute, memory access, and write back. And typically, the point where you take the result in your test bench is when, for example, the result of an execution is writing back to a register file. So if it is writing to register R3, you would actually tap that value and show what is the result. For memory accesses, for like stores, it's basically the bus that is going out onto the memory. For loads, it is the bus again that comes from the memory into the register file. So that's where this register file inputs, which you can see here, or you can see the write back data, right? The line at the bottom, that is where you get the result of your instruction execution. And if you just compare, you will be basically able to find verify the output of the DUT against the ISS. Okay, so this is a very quick example of simulation where on the left-hand side, I have the RTL simulation, and on the right-hand side, I have the simulation from the model or the ISS. And they look exactly similar. This is a passing case. For example, the second column is the program counter or the address. Then you have the opcode, and finally you have the results of each instruction, right? So for example, the first instruction is reading from a memory address and updating the register R13 with the value 7FFF. The same thing is happening on the model. So this is how you actually verify that the two things, whether the RTL and the ISS are exactly the same, giving the same result in a lockstep compare mode. Now, the comparison actually you can do in two ways. You can do it at every instruction step, or in a case of multi-issue processors, every n instructions. So in that case, you will use a DPIC to call model on every instruction completion and compare the result. This actually is a better option because it generates the failure instantly while the test is running. However, you can also run the test to completion and then run the ISS model separately and compare the traces. As long as you can make the two traces equal, you can actually run them. Now, that is also not bad because sometimes what happens is, and you're just seeing here software execution. Much of the problem is when you have external events coming in, like interrupts, debug, triggers, all these coming in from external world. It's easier when you have the full simulation in place for you, and then you can reorder events, right? And then uh, comparing the traces against each other becomes slightly easier. Of course, the flip side is you have to run the entire simulation in RTL, and then you run the entire simulation in model and then compare. But because verification test cases in many cases are not too big, you can afford that. So both are good, but it depends on each who wants to do which method. Okay. So now coming into, we just talked about you did all these instruction verification. Now, how do you handle asynchronous events like interrupts and exceptions? In a random test case, of course, in a directed test case, it's easy, but in a random test case, it can be very difficult. The main problem is depending on the processor, processor can be quite complicated. There's no guarantee you can stop the processor at a precise point by putting an interrupt at this point in time, right? Whether it's an interrupt request or a debug request, your processor may not stop at that point depending on what is going inside the pipeline, right? It will stop at a proper point where it is able to take the interrupt. And that can be quite variable depending what is the design. So it's very difficult to apply interrupts, exceptions from outside and precisely halt your simulation at a particular point. So one of the techniques that we use a lot, and you can always do, is to not trouble the random test case generator with things like interrupts and exceptions, but apply them at runtime. But when you apply them at runtime, your actual uh, program flow would differ from what your random test case generator did. But you can always use what is called a recoverable exception handler, right? So as long as you go into the exception handler, you do something, but you recover to the previous state from where you started the exception handler, it won't deviate. And so you can do another post-processing so you can do a two-pass flow and still the state, you can get the test to pass. So in this way, the random test generator need not be aware of interrupts and exceptions. You need to synchronize the model according to the RTL simulation events. Synchronizing the model is easy because the model is just ISS and you can put it exactly at the precise point. But wherever in RTL the interrupt is happening, for example, interrupt comes, you gave the interrupt at instruction number 95, but it actually took the interrupt at instruction number 100. You need to apply the interrupt to the model at instruction number 100, and then your logs will be same, right? It will exactly match with each other. Now, once you do that, you need to separately verify your handler execution. And for that, especially things like entry and exit of a handler, right? You typically get bugs in the first instruction of a handler or when you do a MRET at the end of the handler. So that you need to separately verify using random test cases. This is a very simple example of a recoverable handler. Don't go through all this there, but I just wanted to mention here, like started off with a state of R1 and R3, and then these are registers. And within the handler code, we make sure we save these registers. In this case, I have saved it into some scratch registers. And then before you do the MRET, you recover back those values in R1 and R3 so that once you do the MRET, you get the same state that you had at the start. Now, this is a very nice and simple way to make sure you use recoverable handlers in your processor verification and not corrupt anything. So it does not alter the state of R1, R3. Also, you can also avoid, if you are doing a lot of randomization, it's also good to avoid memory loads and stores, because they can cause exceptions also in your random environment. So here in this case, we have used, for example, the scratch CSRs. So what I've shown in the figure is what happens when you get an exception, right? On entry of an exception, the RISC-V heart will save these things, like the PC will get saved into the MEPC, the privilege and the interrupt enable will get saved into the M status register in the previous privilege bits and the previous interrupt enable bits. This was what I was showing you in the slide earlier. And all this happens atomically, plus the M status MIE becomes 0. So so it doesn't take the next interrupt, because otherwise another interrupt can come and corrupt your handler. So all this happens atomically when you enter a handler. Uh, so just remember, you can disable an interrupt, but not a synchronous exception. The MIE will stop interrupts, but not an exception. When you do MRET at the end of the handler, it just reverses the process. So you just, the MRET instruction would reverse the process, and all these previous states would go back to the PC, privilege, and MIE. So this is what typically you end up verifying, and you need to make sure you verify across different types of instructions. Especially at the entry point, you can have many different types of instructions. At the exit, you will typically have MRET, but the instructions around MRET can also matter. For example, what is after MRET, right? If your CPU is doing prefetch, or what is before MRET. So all those things matter a lot. Okay, so just shift gear a little bit, a bit on the random test case generator. This is actually the most important tool for processor verification. And what it does, it actually creates legal test cases based on user inputs. Uh, there are a lot of advanced test generators which have large number of features. For example, we use a tool called Raptor, which is also mentioned in some publications here and there. It has a lot of advanced features. For example, you can bias instruction generation depending on weights. You can bias register selection. For example, if you need to create RAW dependencies, like read after write dependencies, you just randomly throw in instructions, it won't create so efficiently. But these tools will have switches which will actually allow you to create a lot of RAW dependencies. So you can say all my instructions will have a read after write dependency. Or you can have WAR or WAW dependencies, right? So which are anti-dependencies. You are doing out of order core verification. You would want those dependencies to come in. And these are very useful for RISC processors. So most of these advanced test generators will have these features. You can attach weights to every instruction call, how you can have the mix of instruction call. You can have memory address range while generating load stores or generating your programs, because you are making so a big random test for your processor. You need to make sure you take care of all these, right? You don't corrupt program memory with data and vice versa, stuff like that. You can have constraints on register values that you can say, okay, this CSR, this bit should never change, or this should always be 0, and the test generator would take care of that. Specifically, if you see what is a random test generator in a processor world, it is a constraint solver. You have all these constraints in there, and it is trying to basically solve the constraints and give you a legal test case based on your user inputs. So typically we call these uh, random test cases as menus, right? So a menu can be something like, okay, I want only floating point instructions. And based on that, the random test generator would only generate floating point instructions. Now, if you are generating, so the other way of looking at random test case generators are templatized random test case generator. Many people use template-based random test case generator, which are not as advanced as constraint solvers. Templatized random test case generators are not so advanced, and they don't typically hit all these bugs. because the state space of a processor is extremely huge. If you just try to say randomize anything, you will never be able to hit those corner case bugs. So you need to go and direct these random test case generators around certain areas, right? And that's where, like, I want to focus only on floating point, for example, or I want to only focus on floating point division, just as an example. So this is how you can actually target specific areas and catch bugs depending on what you want to do. But if you start with a totally like arbitrary random test case generator, the probability that you will find that floating point division bug is very rare, even if you run for months. So these are just a very quick snapshot. I mean, there is a lot of different, in the RISC-V world, there are more and more random test case generators that are coming up, but this is the most important tool for verifying a microprocessor, according to me. Okay, so now quickly shifting gears, we are going a little slow, so let me quickly do. I'll briefly introduce how do you verify memory subsystem, simply the caches, right? So here I have shown a very simple example, iCache, Harvard architecture, Dcache, iCache and Dcache, and there is a MMU in between. MPU is referred to as PMP in RISC-V that I said. In most architectures, as you know, they employ physically addressed cache in the microprocessor world because of maintaining coherency is easier. A parallel access of MMU and cache is possible by ensuring that the lower bits of your virtual address and physical address are same. So either you tend to do higher associativity in L1 or do some page coloring in your OS, and you get parallel access of MMU and cache. So I don't want to go into MMU and all this, but I'll quickly touch upon two very powerful techniques in cache verification. This is what I refer to as how do you verify a set associative cache. Almost all caches in modern microprocessors are set associative. So 2-way, 4-way, 8-way. These are the very common ones. 16-way also in the first level and higher level. The very easy way, or the very what we call as the hot index test, right? You don't try to fill up the cache and randomly do things and try to verify it. We won't catch bugs. What you typically tend to do is create random addresses targeting a specific set. Like I have shown as a red thing here, you're targeting a specific set across the 4 ways, but you need to create address groups which are slightly higher than the number of ways. So if you have 4 ways, create either 5 address groups or 6 address groups. What you will do is you'll get 70-80% hits and 20-30% misses. If you do too many random addresses, everything will miss. So by this, you can have a very nice mix of random hits and replacements. And you can also extend it if you have misaligned access support in your microarchitecture. You can actually extend it to 2 consecutive cache lines. So this is a very powerful way of verifying your cache, which we typically use. And also, I think it's also popular in the industry. This is also some sort of a power attack in the cache. I have seen that people use these type of accesses to do a power attack side channeled. So this actually is very powerful for verifying uniprocessor cache. So you can either do at a unit level, you can do at a top level. If you do top level data cache, it will be load stores. If it is iCache, you will pretty much be doing jumps and loops. iCache is a little tougher doing top level because you need to take care with all the jumps. But data cache is pretty simple to do from top level. You can just do any sort of load store with a hot index, and you will find a lot of bugs around replacements and misaligned accesses and all things coming together, right? The read and the write and the miss, everything colliding with each other. A bit on the cache coherency verification. There are many ways, like what is cache coherency? Like I've seen a very simple example, 4 CPUs colored blue, red, green, black, and it's trying to access the same word in this form, in a form of a cache line. The objective is that each core should see the latest version of data for a given address, right? It should see the correct value. And there are different types of cache coherency protocol, starting from the simplest three-state protocol, MSI, modified shared invalid. You can have MESI, where you add the exclusive. You can have also things like MoESI, where you things have ownership bit also. So for cache coherency verification, you do there are a lot of stuff, right? The companies doing cache coherency verification testing. You do state machine checks, you do formal methods, you do data checks, a lot of stuff. What I am going to show you is how do you do very simply a cache coherency verification with static checks, right? It's almost like templatized. What we do here is, for example, these are four CPUs, right? Blue, red, green, and black. You need to create random non-overlapping addresses in the same cache line from different CPUs. The reason you create non-overlapping addresses is so that there is no ordering requirement here, right? And once you do that, the crash line granularity typically is 32 byte or 64 byte. It's always higher than word granularity or even byte granularity, right? So this same cache line will be running around all the cores and main memory. So you can do random read writes and load stores from each of the CPUs. For example, the blue CPU can write to that blue part, the red CPU can write to the red part, and so on. And what we are actually utilizing here is false sharing, right? There is no true sharing here because all the words are different. So it's actually legal from a software perspective, right? You can, if you had shared, you need for a weak consistency model, you need barriers and you need knocks. But here it's not true sharing, it's false sharing. But you utilize false sharing to stress the cache coherency protocol. Now, false sharing is a problem for microarchitects, right? They dislike it. And normally not many programs will have it. But with false sharing, you can stress cache coherency verification very simply. Each CPU would read write its own set of addresses, and it's almost a static check, right? Every CPU knew what it wrote. For example, the blue CPU knew what it wrote in the blue part. So the final result is the blue part, right? It has nothing to do with what the other guy did. But with false sharing, you can do a lot of testing on the cache coherency stuff. So this is just a simple example. Not everything can be tested with false sharing, but a lot of it can be tested. So just to give you a flavor of how you do cache coherency verification with some architectural tests. Typically, you should try to do verification understanding the architecture and not doing verification dumbly. You'll end up getting into a big mess. So finally, I will go to the RISC-V debug specification. Debug is another very important part of your processor, and it's not the traditional part to verify, right? It's a little bit weird. Debug is something external, right? You attaching a debugger to your processor, and that debugger is used for like halting and resuming your processor or single stepping. You can do program buffer execution. You can read write into a register. You can set breakpoints through triggers. You can set watch points, all these things, right? Now, the debugger is somewhat different from a processor. It's somewhat like a normal hardware IP, but the complexity arises because the debugger is interacting with the software running on your RISC-V core. So there is this external entity which is trying to do all these things, plus there is this software running on your RISC-V core. So this interaction provides to be quite complex, and there aren't too many very good solutions in the market to do debug verification. So I have listed down some of the debug verification challenges, like the different privilege modes you can have. The CPU can be in different privilege modes. You can have mix of instructions in the core pipeline. You can have external stimuli coming in, not only from the debugger to halt and step and all these, but also things like interrupts and bus faults. For example, when you are single stepping, you may get an interrupt, or if you may get a bus fault trying to do a load and store. So all these combinations can be a very difficult. You have to verify this, right? So it's a combination of all the CPU events plus bombarding it with debug requests randomly. And so this is where all the complexity can come in. And in a debug session, user can modify registers, memory. It can execute separate instructions from the program buffer, right? So this is very difficult to achieve with normal constraint, normal random generators. You need special modes in your random generator to make sure you can actually embed debug sessions in your random test cases. For example, in our random test case generators, we have embedded debug sessions, and you can actually if the debug session is modifying the state of your processor, you need to do that. If it is not modifying the state of your processor, you just do single stepping, you just do getting into the debug and resuming or just setting a breakpoint, then you don't need all these. You can do it at runtime. But if you want to modify the state of the software while doing debug, all these things need to be done. And then you also need to ensure that it all checked against the functional model. That means the functional model, you also need to understand all the debug stuff. So this is a this is a test bench that we have for debug verification. The debugger is basically the debug sequences are coded in UVM with constrained random debug sequences, and it's coming into the debug module. Then the other thing is the random test case is getting loaded into memory, and then by the interaction of both of them, you get the traces and then compare against the model and do a pass and fail. Uh, we had a paper in DVCon 2023 on a very random test case generation and verification of debug unit for a RISC-V processor core. In the interest of time, I will not get into too much details, but what it can do is it not only can do simple things like halt, resume, single stepping, it actually allows you to randomly halt a processor in debug mode, change the state of the processor through the debug session. So you can have embedded debug sessions and then come out. So these are the type of complex things our random test case generation and verification can do. And this is a paper in DVCon last year. And if you have interest, you can go through that. Okay, so finally to wrap up and have some few minutes for quick Q&A. So the verification of a modern microprocessor is a complex task. We just finished all the verification in 25 minutes, but it's a complex task. So functional coverage typically would include all instructions and operands, right? And it can also include all operand values. For example, you are looking at a divide algorithm or a multiplication algorithm or a floating point unit. You need to make sure you cover all the types of operand values, including subnormal number and all these, right? We also do things like pairs of instructions or an n window of instructions, depending on how big your processor is. Because it's not only that this instruction is executed, what is behind this instruction and in front of this instruction, that also matters. So these pairs or n window of instruction, that also is very important to track in functional coverage, that you track all these, right? You need to do what is called exception coverage. For example, what are the types of exceptions that are happening in what states and how much of it you are covering. You need to do debug coverage, like just what we mentioned. Did we do coverage of single stepping in debug mode and triggers under all conditions and stuff like that? There are things like cache coverage, because we talked about cache few slides back. Did we go through the state of did we go through like every cache line, go through all the state transitions? Have we gone through all the different coherency protocols in a cache state that is required? So all these type of functional coverage metrics are required. And typically, even for a very simple embedded microprocessor, you would end up getting 1 trillion random simulation cycles. Slightly on the higher end, you will get 10 trillion random simulation cycles, apart from doing things like emulation and running it on FPGA, running large benchmarks and stuff like that. What is important here is scaling the verification methodology to various kinds of processor is extremely important for engineering efficiency, because you wouldn't be designing and verifying the same processor ever throughout, right? So today you may have a 3-stage pipeline. Tomorrow you will have 5-stage pipeline. Next day you will have dual issue cores. Next day you will have multi-threaded cores. Later on you will have out of order cores, right? So that's how everything goes. So you need to make sure when you design your verification methodology, it is not tied to the architecture so deeply that you can't port it to the next level. So that is why we verify a microprocessor understanding the architecture and not going by the hardware spec as a normal IP. RISC-V architecture being open source has enabled a lot of the newer players, improved methodologies, new startups in the processor verification space. Uh, 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 some of you are already aware of many startups, including startup companies based out of India. Simon himself is here, I see. So he can also talk of it. So formal verification is also extremely becoming popular in the RISC-V world. There are two, uh, I would say, different directions. One is the ISA verification with formal tools, the RISC-V ISA verification. The other is data path verification. We use a lot of data path verification, specifically when you are redesigning or designing your FPU or some of the data path. Data path is notoriously difficult to verify with simulation vectors. So you end up doing some of these formal techniques. There are new tools that have come up with data path verification from some of the major EDA vendors, and these are not the same engines as you normally do a control formal verification, right? So these are newer developments that are happening and being adopted in the RISC-V world. Okay, I think that's it from my side, and I'm ready to take questions.
Okay. Thank you, Saurabh, for such an informative talk. Yeah, so the floor is open for questions, please. Yeah, so I see one hand raised from Rajesh Tyagarajan. Kindly go
Hi.
ahead with
Yeah.
your question.
Yeah. Hi. Thanks for the session. I wanted to know how the cache performance is verified. For example, it can be a hit, it can be a miss, but the data can be the same. So, are you
Mhm.
also focusing on performance?
Yes. So I
Okay.
did not talk about performance verification because that's another very big thing, right?
Yeah. Yeah.
So cache verification can be a very big field, including things like replacement policies, including things like bandwidth. So, for
Mhm.
example, there are standard benchmarks, for example, to test. If you may have heard of LM bench, you can run those benchmarks and verify that what is the latency to your first level cache, what is the latency to your second level cache, what are the bandwidth, read, write, all these type of bandwidth. So there are standard techniques and standard benchmarks to verify cache performance, and we
Mhm.
utilize those to do cache verification. Hit miss is definitely there if you have a customer code, right? And you have a target, like your L1 should have only 2% or 3% miss, your L2 should have 20% miss. That you can target. But for a general purpose thing, like you want to do cache verification, things like LM bench is also very powerful, which is more like memory latency bandwidth test.
Mhm. Okay. Like, is it possible that each axis, the hit and miss is being checked in terms of the
Correct. Yes.
latency? Okay.
Yes, yes. So we do
Okay.
that. We have cache checkers. We have cache
Mhm.
latency checkers.
Okay. Okay.
So if there is a hit and you say, okay, every hit should be minimum like 2 cycles, not
That's
more than two
yeah, yeah,
cycles,
yeah,
right?
definitely. Yeah.
So you can put that in your checker, and anytime it takes 4 cycles, you
Means it is a
fire a
miss,
red flag.
probable
What
miss. Yeah.
caused that hit to? So normally miss doesn't matter too much because
Correct.
anyway it's
Correct.
going to take another tens of cycles. But the hit latency is extremely important,
Yeah.
especially at the L1 level, because you get 1 cycle extra, you get 20%
Yeah.
performance loss.
Maximum 2 clocks. Yeah.
Yeah.
Yeah. And where are this documentation? You said the LM bench something you said, no?
LM
Uh,
Bench you can search on it's something that runs on
Stand.
Linux. You can
Okay.
download LM Bench, run it on your laptop or run it on your machine, and it will tell you all your cache sizes and all the stuff, cache
Okay.
memory bandwidth. Yeah.
Yeah.
I think it's a paper in Usenix conference from long back, maybe 20 years old or something. You will find the original LM bench papers also. There are multiple benchmarks which are derivatives of the LM bench only, but I like LM bench a lot, so I just mentioned that.
Yeah. Thanks.
Yeah. Any further questions? Okay, seems like there are no more questions. So once again, thank you, Saurav. Really
Yeah.
appreciate your time and such a nice and engrossing talk. Yeah, as I mentioned, this call has been recorded and will be posted on the IEEE SSCS Daily Chapter website. So folks can go and review it there. So thank you very much once again, and it's time to close the session now. Thank you.
Thank you. Thank you, everybody, for attending.
Bye bye.